All right, so there is an equation that describes centripetal acceleration, and the proof for it is kind of long and complex and doesn't really add, in my opinion, a ton to your understanding of physics. If you are curious about it, you can YouTube it on your own. Often, the people who prove it use calculus, so that's another reason I'm avoiding it. There's a non-calculus version proof too, but anyways, so I'm not going to do the math proof. I'm just going to do a conceptual proof to help us understand where this equation comes from, because it's that conceptual understanding that they're really going to be looking for on the AP exam anyways. And if you ever need the formula, you'll have it on your formula sheet. So the first thing that I'm going to talk about is let's talk about a couple different types of turns that you could do. The first type of turn you could do, we'll always start from this right-hand side as our initial velocity points. The first turn that you could do is you could do, let's start down here. Let's do, we're making a very slow turn, so our velocity vector is not very big, around a very big curve. And then I'm just going to move forward about, let's see, it's about that much. So we're about here, we'll say. That's about how far my velocity vector would get me if we moved that far in our period of time. So you can see that if I compared these two velocity vectors, I'm going from something that looks like this to something that looks like that, and I would have an acceleration that looks approximately like that. Kind of a small acceleration, just enough, just a little bit required to change a vector from going straight up to going a little bit to the side. But what happens if we speed up a little bit? What happens if I roughly double, and I'm definitely eyeballing these kind of things, roughly double my velocity. So then I would be, I don't know, around here after the first second, because I'll have traveled a little bit bigger distance, and I'm going to try and make my velocity vector approximately the same length. And there we go. If I did that and we compare these two velocity vectors and we want to figure out how much acceleration it's going to take, I'm going about there and then, yeah, I don't know, there-ish. And to turn this velocity vector into that velocity vector, you can see that it requires a lot more acceleration. But that's interesting. Well, we'll talk about why that's interesting in just a moment. Now let's go. So hold on. This, well, I guess it's obvious, but this one was fast. This one was slow. I'm going to do another slow one. So same speed, roughly, this like 1 unit, but because it is a smaller circle, we would have gotten all the way around there. So when I draw this in, my vectors are going to look more like this. And you can see that that creates a pretty significant change in acceleration, change in velocity. And finally, if we go fast around a small curve, let's just say that roughly we get to there and we'd have a vector that was originally going this direction and is now going that direction. And to turn this vector into that vector would actually require us to take away 2 and add 2 more in the negative direction. So that's all the way, oops, I'm going to have to put that on the other side so I have some space to actually draw the whole vector. So it would be a vector, well, that's not the right place to draw it either. Let's draw it here. I have to take away those 2 and then add 2 more in the negative direction. And you see that that vector is now huge. So what comes out of this? The understanding that if we're making a slow turn, then our velocity vector doesn't have to change by very much over a period of time. It only has to go like a little bit. But if we're going faster, not only does our velocity vector have to change by more because it's already longer, and changing a small vector from here to here isn't a big change, but changing a big vector from here by the same angle creates a much larger arc near the top. So going faster means just by the nature of like vector quantities, we're going to be shifting more. But it also means that you're going around the circle even faster. So not only are you trying to move a bigger arm, the arm itself is moving faster around the circle. So it turns out that if we're talking about an equation for this with acceleration and we want to figure out how velocity affects it, it makes sense that as velocity increases, the amount of change, the acceleration required, has to increase. But if we look at the other side of that, we look at the difference in sizes of my circles. If we have a big circle, then we didn't go very far. It wasn't required to change as quick, but that small circle, because even after like 1 second, you've moved really, really far around your circle, and your vectors had to shift a lot to keep you going in that circle. So as the radius gets bigger, it requires less acceleration. So if we were trying to figure out how radius affects it, a bigger radius needs a smaller acceleration. So that means that the r is going to go on the bottom because these are inversely proportional to each other. The only other piece that I have to throw in there, and this is where that big change of like, okay, velocity to here makes it a difference if it's bigger, but also if you're going round, is it's actually a v squared concept. So this is the formula for centripetal acceleration. And the last that I want to mention is just some quick graphing tips. If I was trying to graph this, what you might graph is RAC versus V squared, where you're trying to do something like you're changing the radius and seeing how that affects the velocity, the max velocity before you fly off the road. And if we did that, we might graph V, V as our independent quantity and R as our dependent. But if we did that, we would get an exponential curve. So what we'd want to do instead is graph v squared versus r. And then when we did that, we would get a linear graph, and our centripetal acceleration would actually be the slope of that graph. The other option is that we could graph v versus the square root of r, and then our slope on that would still be a linear graph, but then the slope would be the square root of our centripetal acceleration. So that's just a little bit of a discussion just to get you primed and still thinking about linearization, which is a big skill that we're going to be practicing. But the big takeaway, of course, is this centripetal acceleration. So thank you for watching and have a great evening.